Hello all, this is Satvik and this video we will discuss about Ret2libc. So Ret2libc is a binary exploitation attack where you could pop a shell even without having any sort of system function within the source code. So let's discuss what libc is. So we actually attack a module called as libc. This is like a library within C. So even though you write a hello world program, this libc is loaded by default, and this libc contains some important functions for your program to run, but also some other programs which you can use as an attacker to gain a shell. For example, a system function which helps you to load some binaries and stuff like that, and there is a bin bash hard coded within your libc which you can further utilize to gain a proper shell on your vulnerable program. So I'll leave the link for this Ret2libc in the description below. So this is it does have like some lot of headers and some basic things that your C program does require to run. And let's come back to the source code, and this is my source code and it is intended to be vulnerable again. And you can see we are using gets function, and this doesn't have any call of like system of bin bash or anything like that. And there are some other programs. So some of the guys asked me in the previous video that rewriting the EIP is not that crucial, but sometimes there might be some functions. For example, if you take embedded systems, there are a lot of system calls like bin bash and stuff like that. And if you are able to rewrite the EIP to the function which does contain that system call, then you could actually get a shell. But here in the Ret2libc, you don't even need that. You don't even have any system within this. And you can see this is a very standard program where a buffer is gets it is getting read through gets, which is vulnerable. And also I mentioned process to execute, so I'm compiling it to a binary called main, no stack protector, meaning that your stack is executable. So this is something. And no pine, no randomization, and 32-bit program. Just you can also do this on 64-bit, 32-bit just for easiness for our eyes. And the -G for debugging. It's very useful when you are actually learning the binary exploitation, because if you don't enable this debugging option, it's just the same assembly code, which is kind of headache sometimes. But if you have an access to source code, I would strongly suggest you to use this debugging option, and it will help you make your job easy. And I'm making this to C99 because in the latest versions of C, gets is kind of vulnerable, and it's not allowed. So I'm just making this stuff like this, and I'll make the source code and the binary available on my GitHub repository. So let's go back, and this is uh, my Windows subsystem for Linux, and you can see I have main binary here, which is compiled from main.c. And if I do a checksec, so checksec is a very good function tool to see what all, sorry, so you can see what all protections are enabled. Stack canary is not found, not executable is disabled. So in the sense you can execute things, no randomization and some other things. I would mostly check for the NX and randomization and the stack canary sometimes, because those are some things that are very useful. And let's do the GDB part. Let's see what we can actually do. And I actually did some kind of hard work for you guys and identified where you can rewrite the buffer and all, but I'll do it once again. So let me launch the GDB/1, sorry, main. Sorry, I'm just get used to the one thing. And I'll set a breakpoint to main just to keep simple. Or you can delete breakpoints. I think you don't need a breakpoint, just to identify where your RIP or EIP is getting rewritten. So our goal again here is to rewrite the execution pointer with the system address and followed by some bin bash, so that you can actually get a shell. But before that, let's see where your instruction pointer is getting rewritten. Let me do something like run, and if I paste some input like this, you could see my EIP is actually getting rewritten with this couple of b's, and this is where I identified this. And also if you want, you can just do something like cyclic pattern create, sorry, pattern create 90, for example. Just copy this, run it again, paste it, and see where it is actually coming up, and search where it is coming there, and just calculate this with using some pi or something like that. Okay, so this is how you can do it. So now we actually have all our things required, like where we need to set up our EIP and all. So let's see some more functions and all. So now let me set the breakpoint to the main, because I just don't want to execute the whole function. I just want to see how the memory modules are loaded and stuff like that. So if I do a run now, it's not going to execute and give me the prompt where it is asking me for the input. But now if I do a command called vmmap, it shows me all the modules that are actually loaded, and you can see main is being loaded. That's good. And there is something called as libc here. So this is what I was talking about, and this is the base address, and this is the offset and other things. I would actually use this base address because it is going to be useful for us. And also you can also use something like system, and this is actually printing the system address for you. So if you can do some kind of like a thing, this actually has some kind of similarity with the starting point of this libc. And also do take this particular starting address of the libc, not the second one, because don't assume that executable doesn't mean you should start taking from this. You should actually start taking from this. So this is going to be your start address of your libc module. So that being said, it's cool. And we'll also see the exit. I'll tell you why we actually use exit too, and let me note these things somewhere. Okay, and also the exit. You actually don't need exit. You can also use some random data, but I'll tell you why I particularly use exit sometimes. And that being said, you can also do some bin sh, but it is not useful. It's not useful, and it doesn't show up all the time. So one thing we identified is the location, the exact path of where this libc is loaded. And as I told you, libc also contains some hard-coded bin sh, which we will be using. As the libc is loaded into your binary, we can actually make use of that bin sh and pop a shell. So you can do something like strings -atx and the path, and you can see these are some address which is kind of like a normal address which get appended to the start address of your libc whenever your program is loaded, and that is going to be your address. So I'll try my level best to explain this as best as I can. /bin/sh, and you could see this is the address. So now let's go back to the gdb, set the main breakpoint to the main, and if you do run, it actually something does like this, and vmmap again, and you can see the libc is again loaded. Let's do some basic thing here. So in order to actually find the address of your bin sh in this binary, you should add the address, that the hard-coded address that you got from the libc module, which we identified through the help of strings, with the start address of this. Let's convert this to hex. Now we can actually examine the memory using this to verify if this is actually bin sh, which is going to be x/s. This is just for examining the memory, and you can see this is actually pointing to bin sh. So the one thing we did was, like, we identified the base address of your libc, and we identified the hard-coded address in the libc module using the help of strings. And I actually added both that, because that address is going to get appended to your base address or the start address whenever your program is executed. And adding both will give you the exact path of your bin sh. So, and also I verified using x/s, and I'm sorry if this text is kind of blue and it's kind of hard to read. So that being said, we have all the addresses: system, exit, and bash. So the process of passing the payload is, buffer, which is going to be our 76As, and the system address and the exit address. This exit address is actually not required. You can also pass, like, as this is like a 32-bit, you can pass like 4 Bs or 4 Cs or some random data just to fill the details. But if whenever you identified an exit address, just try to pass it and see, because exit helps you to gracefully exit the system call. So that's how it is. And I'm actually trying to do a lot more research on why exit is used, but it should actually use if you pass something like sorry if you pass something like 4 Bs or something like that. But as we already have exit here, we can actually use that. But anyways, this should work fine too. And that being said, this is an exploit written using pawn tools. So I'll just give you what this exploit does. So importing, and I use the system addresses, and also I verified them again by running the program and going through the X slashes and mentioning this particular address, and it should show you the system or exit or bash. And then I went with the buffer. I actually did hard coding myself, but you could also use something like p32 of system. We should actually do the same thing, but anything should work fine. And then I loaded the process, send the payload, and p dot interactive to get the shell. So this is how you actually exploit this return to libc. So the reason why you are passing exit is just to gracefully exit the program. If you don't find exit function, then just you can simply use something like a couple of b, something like this, and that should actually work for you. And also, if you are interacting, so this, if you are playing a ctf and if you find it interacting with some kind of a server, then please check out my previous video on introduction to pawn tools, where I mentioned how to use host and remote to connect to the different server and send this payload. That being said, this is everything regarding the return to libc, and in the next video I'll try to show you a cool ctf challenge from the archives, and show you how I could actually exploit this return to libc in wild. And that being said, thank you for watching this video till the end. This is Satvika. I'll see you in the next one. Bye, take care.